We're going to move on now and talk about some other interesting aspects of electrochemistry. And one of the most necessary and useful applications of electrochemistry is the concept of a battery. And this is just one of many battery designs that have been used. And what you can see if you look at this is the top, obviously there's a metal cover, and the bottom has a metallic cover to allow for the free flow of electrons. Centrally, you have a carbon rod which acts as electrode, and then on the outside you have a zinc rod which also acts as electrode. And between those two you have what's called a porous separator. In between those two is a paste that's made up of manganese oxide, ammonium chloride, zinc chloride, and water. And this allows for the transfer of electrons to the zinc ions and so forth. So this is just one of many types of battery constructions. A battery is anything that acts or produces an electrical current. It's an electrochemical cell that produces an electrical current. A primary battery, or a dry cell, is a battery that has a single use and cannot be recharged. The diagram is a cross-section of a simple dry cell battery, zinc carbon dry cell battery, that's frequently used in a flashlight. Now, another type of battery are alkaline batteries, and they're designed as replacements for the zinc carbon dry cells, and they have a better performance characteristics, and that's why they're used. You see the design is very similar. You have the top and bottom made of metal. You have the electron. Now in this case the electrode is coming from the bottom as opposed to the top. You have the zinc powder in the middle and a separator, and in between, the separator separates manganese powder from a zinc powder. And so this design allows for more charge capabilities, which is what batteries are basically based on, how long they last. Now, here's another type of battery that's designed as a, quote, jelly roll. And what you can see here is the different electrodes are wrapped around each other, and in between is a separator. So you have this sort of jelly roll configuration, and you have multiple electrodes that can react with the separator in between. Now, this type of configuration allows for something called a secondary battery. Now, secondary batteries are batteries that can actually be recharged. So you use them up, then you put them to an electrical current and essentially reverse the reaction by adding electrons, and the battery recharges and you can use it again. So this is a nickel-cadmium battery. The nickel and cadmium are the two electrodes that are jelly rolled around each other with a separator in between. And this significantly increases the amount of current that can be delivered compared to a standard alkaline battery. Now, recently the most common batteries that have been used are lithium-ion batteries. And this is to show the way in which lithium-ion batteries are put together. The charge flows between the electrons as the lithium ions move between the anode and the cathode. And this is what you can see in this diagram, is the motion of the lithium ions, which are the little plus balls in the middle here, traveling from the positive electrode, which has metal, oxygen, and lithium ions, and the negative electrode, which has these graphite layers. The lithium ions travel, and at the same time, negative charge travels in the opposite direction and causes the discharge. This is a lead-acid battery. Lead-acid batteries are used in cars, and they consist of six cells that are connected in series. Each cell has 2 volts, so if you connect them in series, the total voltage is the sum of those volts, and you end up with 12 volts. They're used because they're very low cost and they put out a huge amount of current, sometimes as much as 400 to 800 amps of current. They're not very practical for some things because they're large and heavy, but because they're being used in cars or boats, their size and heaviness is not prohibitive. And this provides the power to start engines. Now this is a diagram of a fuel cell. Now a fuel cell is not the same thing as a dry cell or what we just looked at with the lead cell. A fuel cell is a device that takes a chemical reaction and converts that chemical reaction into electrical energy. It's similar to batteries, but there has to be a source of fuel that undergoes the chemical reaction and produces the electrons that are necessary to cause the electrical energy. So on the left here you have hydrogen ions entering into, that's the fuel. On the right is oxygen, which is taken from the air. And the oxygen is reduced and combines with the hydrogen, which is oxidized, to produce water. And the water is then removed in the form of water vapor. And with this process, electrons are produced, and this causes or produces electrical power. Fuel cells, because they use hydrogen, their only exhaust is water vapor, so they are very nature friendly, as it were. So that's the positive idea, or the positive thing about fuel cells. There are actually fuel cell cars that can be bought in California. I think that the Hyundai produces a fuel cell car, and I think Toyota produces a fuel cell car. But you cannot get fuel cell cars everywhere because you can't buy hydrogen everywhere. And hydrogen is somewhat the downside because hydrogen is explosive. I don't know that it's more explosive than gasoline, but it is explosive, and if it catches fire, it will blow up. This is a hydrogen fuel cell schematic. Oxygen from the air reacts with hydrogen, which is produced as fuel, and ends up with water and electricity. So it's very environmental friendly from that perspective. Now the other process that can occur is something called corrosion, and we all recognize the term corrosion. We think of it in terms of rust. And what we're looking at here is 2 different pictures of the Statue of Liberty. And the first picture on the left, A, is the Statue of Liberty when it first arrived, or early in its history when it arrived in the United States. And you see that it's a dark color because it was made of copper. Now you see the Statue of Liberty, which is shown on the right, has this lighter gray, sort of gray-blue appearance. That's the corrosion that has occurred over the years. So corrosion is the degradation of a metal due to an electrochemical process. So the picture A is the Statue of Liberty, which was covered by copper and was originally this brown color, as shown in the painting. But now, because of exposure to the elements and the ongoing corrosion, you see that it has this blue-green look. Patina is just sort of the look which you see when you look at it. So corrosion is essentially, as it says, an electrochemical process. So you have a cathodic site and an anodic site. The anodic site is the oxidation site, and the cathodic site is the reduction site. So you see what occurs at the reduction site is when there's water available and electrons can flow, then the oxygen in the air is reduced to form water, and when those electrons move, then iron goes from solid iron to iron 2, and combines with oxygen to form the corrosion that you see. So what they're talking about here is that most things are painted to prevent corrosion, but once the paint is scratched in some place so that the iron surface is exposed, then the corrosion begins to occur and rust forms. And the speed of this is increased if electrolytes are present, which facilitate the flow of electrons. And this would be things such as sodium chloride, which is put onto roads to melt ice, which is why the salt water is good to wash that off your car, because it decreases the corrosion on your car. Now, there are several things that are done, but there's a way to try to prevent corrosion for something you want to prevent. And this is one of those ways that you can try to prevent corrosion. On the left is the material you want to protect. So let's say that this is an underground metal septic tank or some other underground tank, and you want to try to prevent corrosion in this tank. And you can paint it, but you can also do something called that's shown here. And what they've done here is they buried a second piece of metal called the sacrificial anode. And the sacrificial anode is a more active metal. It's made of a more active metal than the tank. And you connect those two with a wire such that the more active metal will become the anode where oxidation occurs, and the tank becomes the cathode where reduction occurs. And since reduction occurs, that preserves the metal, prevents the metal from oxidizing. And so this is called cathodic protection. It's a means of protecting metal from corrosion by making the object you want to protect a cathode in an electrical reaction. So you have what's called a sacrificial anode, and this is generally a more active metal that's buried near the object you want to protect, because you need to connect the two with a wire. If you can think of this in terms of this original diagram we had with the salt bridge, the wire acts as the salt bridge, and you have the sacrificial anode is where the oxidation is occurring, where the metal's being removed and forming ions, and then the cathode is the tank you want to protect, and you're actually depositing iron or keeping the metal on the tank. And this acts very well and works very well if it's set up properly. And so this storage tank is protected this way, and the active metal is usually something like zinc or magnesium, and it acts as the anode, and it preferentially corrodes, preventing the corrosion of the tank that you want to protect.